In our couple classes ago, we were talking about pH, and pH is a measure of the H plus in solution, and we said these are the calculations you do when you have strong acids and bases. So let's come over here to the picture of this Ka, Kb, and I wonder if we're maybe revisiting and remembering what K kind of represents. Think back to when we were talking about K values. So over to the picture side, I'd like us to revisit the concept of a strong acid and strong base. So a strong acid, let's just say HA, would dissociate completely in solution. So I'm going to draw a single arrow and say it would look like this. HA is dissociating at H plus and A minus only. Now, going back to the concept of a weak acid, which we learned on the second day of this unit, a weak acid does not dissociate completely. So a weak acid, HA, will somewhat dissociate, split apart into H plus and A minus, but some of that will stay as HA, so we need to actually add this double arrow. Sometimes you also see this written as H3O plus. I'm just trying to simplify it here. So now that we have a double arrow, I want us to be thinking about, we now have an equilibrium. And equilibriums have K values associated with them. Okay, let's do the same thing for a base. Oops, let's say strong base. So a strong base, if we had BOH, would dissociate completely, so we can get a single arrow and say it would split apart into B plus and OH minus. And then a weak base does not dissociate completely, so the weak base BOH would somewhat split apart into B plus and OH minus, but some of that would then be reforming into the BOH. It would not all be split apart. So we would have a double arrow now, which means we have an equilibrium established. And these equilibria are what we're talking about when we talk about Ka and Kb. So Ka and Kb are the values, the equilibrium constants we use for a weak acid and a weak base for pH. Okay, now Ka and Kb are used to calculate the pH of a weak solution. So that's where we have them. Now let's go to a weak acid really quick. I want to revisit what Ka would represent. Remember, it's just this concentration of the products over the concentration of the reactants. So for a weak acid HA, which equals H plus plus A minus, Ka would equal the concentration of H plus times the concentration of A minus divided by the concentration of HA. Now remember, whenever we're trying to calculate pH, we want to do the negative log of that H plus. So we need to kind of solve for H plus, which could be kind of thought of as an X. Okay, similarly, for a weak base, Kb will equal, now look over here at the weak base. It looks like BOH is dissociating to B plus and OH minus as the product, so it would be the concentration of B plus times the concentration of OH minus divided by the concentration of BOH. And again, when you're trying to calculate the pH of a base, we could do the negative log of the H plus and then subtract that from 14. But here's what we're going to be solving for again. That OH minus ion, and we could use that or think of that as an X value. Okay, let me go through a couple of practice problems with you now. Calculate the pH of a 1 molar solution of HF, and it gives us the Ka value is 7.2 times 10 to the negative fourth. So I'm going to start out by doing HF dissociates into H plus plus F minus. And now I'm going to set up a little ice table. So what is my initial concentration of H plus and F minus before anything dissociates? Those would be 0. What's my initial concentration of HF? That's 1 molar. We're usually given that in the problem. what would happen to HF as it dissociates? It is going to go down, minus X. What happens to these? These are always going to go up. So we can assume this is always going to be minus X plus X plus X. So our final here would be 1 minus X, 0 plus X is X, 0 plus X is X. And now I have my equilibrium concentrations. I can now set up a Ka value. Ka for this problem would equal the concentration of H plus times the concentration of F minus divided by the equilibrium concentration of HF. Ka was given to me here. It's 7.2 times 10 to the negative 4. What's my equilibrium concentration of H plus? It's X. What's my concentration of F minus at equilibrium? It's also an X. And then what's my concentration of HF? 1 minus X. Now I need us to think back to the equilibrium unit, and which of the two tricks are we going to use for this setup? Are we going to be able to take the square root of everything, or are we going to get rid of that X value? And you guys, this is always going to be the case here. We're just going to get rid of that minus X. We're going to say it's probably insignificant for this problem, and we're just going to put it over 1. So now if you want to calculate what X is equal to, we can just say X squared would equal 7.2 times 10 to the negative 4th divided by 1. So we can multiply that 1 out. And then I'm just going to take the square root of 7.2 times 10 to the negative 4. So I can do square root 7.2e minus 4. And again, I multiplied that by 1. We would want to do that. And I get 0.027, we'll say. Now, we're not done. X is the concentration of H plus. And this problem wasn't asking for the concentration of H plus. It was saying, what's the pH? So pH equals the negative log of H plus. And if I do the negative log of 0.027, I get 1.6, we'll say. And what this does here is this is a little bit higher. If you just took the negative log of 1, that would be lower. So this takes into account that not all of the HF is dissociated into H plus. Okay, let's try a similar problem below for the Kb. Calculate the pH of a 10 molar solution of NH3. Okay, now when NH3 is added to water, it turns into NH4 plus and OH minus. This is just kind of a special reaction I'd like you to remember from earlier in the unit. Okay, now if we set up a ice table here, I'm going to not use H2O in there because that's a liquid and we don't put liquids in ice tables ever, just aqueous and gases, and really all we're going to be doing for acids and bases are these aqueous solutions. My initial concentration of NH3 was given to me, that was 10 molar. Before it dissociates, these are always going to be 0 for these problems, or at least the ones we're doing. So this over here will always go down. These will always go up, so plus X. This value down here will always be that value minus X. 0 plus X will always be X's here. I can now set up my Kb problem. So for this problem, Kb is going to equal the concentration of NH4 plus times the concentration of OH minus divided by the concentration of NH3. Again, I'm not putting H2O in here because that's a liquid and we don't put liquids in equilibrium problems. It gave me the Kb right here was 1.8 times 10 to the negative 5th. That would be equal to X times X. I'm just going to start getting that right in here as X squared, divided by the concentration of NH3, which was 10 molar. So for this problem, we can't multiply this by 1. We got to multiply it by 10. But let's solve for X now. So I'm going to do 1.8 times 10 to the negative 5 times 10. Or we could just do the square root of 1.8 e minus 5 times 10. Oops. And we get 0.013. just going to check that again one more time. The square root of 1.8 e minus 5 times 10, yeah, 0.013. And now, what does this x represent? This x, oops, this one, represents the concentration of OH minus. So if I do the negative log of 0.013, I'm not calculating pH, I'm calculating pOH now, remembering from the base problems. Okay, so what's the negative log of 0.013 is 1.9. And again, that's pOH. This wouldn't make sense to me that a base has a pH less than 7. So now let's subtract that from 14. And that means my pH would be 12.1. Okay, now it makes sense that this is a high pH. Okay, we're going to skip problem 3 over here. And we're going to actually skip the practice 2 problems. And what I'd like you to do now is try the weak acid, weak base pH practice worksheet. I'm going to make a solution video for that. And then I'd like you to enter the answers with your work in the Google Doc I provide. And you can obviously just kind of watch and copy this down from the video, but just try it on your own first before you copy down the answer key. And that'll be our activity for today.